Okay, so in the last video, we were looking at the area between two curves, and we saw an example where we had a region contained between two curves, but the region we were looking at was only in the first quadrant. So I want to look at a second example, and in this case, we're going to look at one where the region is not just in the first quadrant, where it stretches across some of the other quadrants as well. So let's start by thinking about this example. We're trying to find the area between the two curves, y equals the cosine of 2x, and the quadratic function y equals x squared minus 2. As is always the case in questions like this, we start with a good graph. We make sure that our graph is big enough that we can see everything and that we shade the region that we're interested in finding. So in this case, we want the area of this red shaded region between the two curves. Well, as was the case previously, the first thing we need to do is find out what the points of intersection of these two are, because we can't find the limits of integration without the points of intersection. So what we want are these two values here and here. And again, like was the case previously, we do that by setting the two curves equal to each other. And so what we want to know is, for what values of x does the cosine of 2x equal x squared minus 2? But unlike the previous case, we can't solve this function without a calculator. So we rely on technology for this one. We'll be given a calculator for this kind of a question. And so we go into our calculator, and I want to show you the best way to do this in your calculator so that you do it efficiently and don't spend too much time on it. Now, we could go straight over to a calculator screen here and just solve that equation that I had written down. But I know that eventually I'm going to want to see what these curves look like, if for no other reason to check my answer. So I might as well start with that. That's going to be more efficient. So I go to my graph editor, and I want to enter the function y equals the cosine of 2x, and I see it there. And then I want to look at the function y equals x squared minus 2, so I'll just move this label over here. And now I'm going to do my second function. My second function was x squared minus 2. And there's my second function in red. And I want to find the shaded region between those two curves. So the next thing I want to do is get the points of intersection. I want to know what this point of intersection is and what this point of intersection is. And I do that the way I was just talking about. I'm going to set the blue curve equal to the red curve. But I can save a step now because I've already defined these. I already know that cosine 2x in the calculator has been defined as f1 at x. And I know that the quadratic x squared minus 2 has been defined as f2 at x. And so what I want to know is, when does f1 at x equal f2 at x? And I can go back to a calculator screen and I can work that out. And all I do is go into my menu here, go down to algebra and solve. And what I want to solve is, when does f1 at x equal f2 at x? And of course, I tell the calculator I want to solve that for x. And the calculator kicks out these two answers, negative 1.153 and positive 1.153. So I can go back to my graph and I could label those on there now. So what I'm going to do is I'm going to say, okay, my answer is plus or minus 1.153. And I'm going to find this 1.153 number as a. So I'm going to get rid of this plus or minus, and I'm just going to let this equal a. And the reason I'm going to do this is because I don't want to have to keep writing this 3 decimal place number. So I'm going to come up here and I'm going to say this is a, and this is now, of course, negative a. And now I want the integral from negative a to positive a of top function minus bottom function. But again, I can do this a little bit more efficiently because I can see that this graph has symmetry across the y-axis. In other words, the area over here on the left side and the area on the right side are identical. So rather than integrating from negative a to a, it'll be easier for me to integrate from 0 to a and double it. So the area I want is twice the area from 0 to a of my top function. And I go up here and I look and I see that my top function is the cosine curve, minus my bottom function, which must have been the quadratic. Very important that I put the parentheses here because I'm subtracting this whole function. And I'm doing this with respect to the variable x. Now I need the calculator again to solve this. So I'm not going to mess around with antiderivatives because if I'm using the calculator anyway, I might as well use it right from the beginning. So I go back to my calculator screen. And I say, well, first of all, I want to take this 1.153 number and store it into A. So I'm going to get rid of all of this stuff. And I'm going to tell the calculator to take this number. And I'm going to keep all of these decimal places because I'm going to need to be that accurate. If I truncate this after 3 decimal places, I might not get the right answer. So I'm going to store that into A. And now the calculator knows that that's what A is. And now I just do exactly what I just said. I would like 2 times the integral from 0 to A of my top function. And what was my top function? Well, my top function, if I go back to the graph, my top function is the blue one, which is f1 at x. My bottom function is the red one, which is f2 at x. So I can just put it in like that. I don't have to type these functions again. So I'm going to say I want f1 of x minus f2 of x with respect to x, and this should kick out my answer. And it tells me that my answer is 4.332, so I can go back to my question, and I can write that answer in. And I can say that this, now I need to say that this is approximately 4.332, because it's only 4.332 to the first 3 decimal places. There's actually more digits that come after that. Now what I want to do is I want to check my answer. So I go back to the calculator again. And I can go back to my graph screen. And I want to ask the calculator to tell me what this area is. So you remember how to do that. We go up here to menu. And we're going to analyze this graph. And we want the bounded area. So we get down to 8. And we want the bounded area from my lower bound, which was 0. Actually, sorry. My lower bound in this case, I may as well take negative A. I don't know. Let's try this. Negative A. Yep, that was fine. It remembers my negative A. And my upper bound is going to be over here at positive A. So I think I can just put that in. No, I can't. So let's try that again. I want the area between these 2 curves. And so I'm going to go menu, analyze graph, bounded area. My lower bound is going to be this intersection point, so I'm just going to go get it. My upper bound is going to be this intersection point, so I get that. And it tells me that my area here is supposed to be 4.332. And so I go back and I check, was 4.332 what I got? That's the same answer that I got, so I must have been correct. So we see that if we use the calculator, we can do a few things to make that a little bit easier for us by storing these functions into f1 and f2 and not having to rewrite them, by storing this big number 1.153 and all of its decimal places into A, and then just using A and f1 and f2 here instead of rewriting these functions. And so we also notice that it didn't make any difference that one of our curves was below the axis, one of our curves was above the axis, that we were partly on the left and partly on the right. We did it the same way and we still got the answer. So it's always the integral from left to right, top function minus bottom function, as long as we're integrating with respect to x. Soon we're going to look at integrating with respect to y, which is a different way of doing it.